to talk about my career path. So, just to show you, because I noticed a lot of PhD students are presenting in our in this group, so that you can see how you can build on your expertise and how you can use your expertise to work on different problems and how to solve a variety of engineering problems. All right. And my aim was to start my master's degree, but because of time, I decided to start from PhD. But just to let you know that I did work for almost 5 years before starting my PhD and before doing my master's degree as a fluid dynamic expert and hydrodynamics engineer. But then I came to Australia and I started doing a PhD project on environmental flows. My PhD was about flow, turbulence, and mixing in oscillatory canopy flows. So I'm going to introduce to you some of these words. I think oscillatory, many of you can understand what it is. It means that it was a wave-dominated environment. So it wasn't like currents and rivers. It was unidirectional. It was a wave-dominated environment. And canopy, I'm not sure how many of you are familiar with this term, but what I'm referring to here, canopy could be a community of any bed roughness, any large bed roughness. Could be terrestrial forests, could be urban skylines, urban buildings, or could be aquatic canopies like corals and seagrasses. And that was the focus of my PhD project. So why aquatic canopies? Because I think now everybody is familiar that those are extremely important ecosystems because they provide a wide range of ecosystem services. They oxygenate the water. They are providing food and shelter for many fish and invertebrates. By reducing the near velocity, they trap sediments. They uptake nutrients. They help purifying the water. So they provide a wide range of services, but to understand to what extent they are providing the services, we need to understand the hydrodynamic interactions in these environments. For example, if you release a bunch of nutrients, let's say sediment, I don't know, microplastic, unfortunately, something like particles, and if you want to know what happens to those particles, are they going to stay there? Are they going to sink? Are they going to flush out from the system? We just need to be able to predict that. And that was the main question of my PhD project, but when in wave-dominated environments. Because when I started, we had a good understanding of unidirectional flows, but not waves. And it's obvious because wave-dominated flows are much more complex. So we'll always start with simple case. All right, so let's start with some general understanding of canopy flows and how they look like. So if there is no canopy in the system, let's say we have a bare bed, this is how we expect the velocity profile to look like, right? It's a logarithmic velocity profile, almost zero near the bed, and then almost constant velocity far above the bed. When we have a canopy in the system, let's say a seagrass meadow, as I'm showing, the velocity within the canopy reduces from the velocity far above the canopy. Why? Because of the drag exerted by each canopy element. So let's say if the flow is coming with like 10 centimeters per second all over the water depth here, when there is a canopy, it would be 10, and then all of a sudden, I don't know, 5, something. What that means is that at the top of the canopy, we have a very strong velocity difference from 5 to 10 centimeters per second. We call them velocity shear. And that shear creates instability to the system. And because of that instability, we get these large scale vortices. We call them like the Kelvin-Helmholtz vortex structures. Many of you are familiar with this, so no need to describe. Now, in unidirectional flows, like in rivers, those large scale vortices, they dominantly control rate of vertical mixing. So if you release a bunch of nutrients or sediments and particles, these larger scale vortices bring them to the canopy. the canopy either uptake them or they deposit or whatever happens, then these vortices bring them back up to the overlying water. And that's a very important ecological phenomena and question, because that tells us about the residence time in these environments. So yeah, in unidirectional flows, those larger scale vortices dominantly control the rate of mixing. We also have this wave turbulence, which are small scale turbulence generated behind the stem. For many of those doing flow structure infractions, you are very familiar with this. So we also have this in the environmental flows, like the small scale turbulence. They are present, but they are not dominant process controlling mixing, because those larger scale vortices are very strong. Okay, that was all we knew for unidirectional flow. When I started my PhD, the question was whether we could use that understanding or those predictive models to predict mixing and transport in wave-dominated environments, because many of these gases, almost most of them, they are in shallow coastal areas, so they are exposed to wave action. So we really wanted to know if we could use those understanding, and if not, how we really predict rate of mixing in coastal canopies. All we knew was that those larger scale vortices are actually present when we have waves. Okay, so here I'm showing, let me change my, yep. Those larger scale vortices are present. So this is a PIV testing in the laboratory. So in the bottom, you may not be able to see, but there are canopies. We use rigid dowels to simulate the impact of the drag of the canopy. So on the bottom here, we have canopy, and then it's, we injected some particles, and you can see the flow is going back and forth. I'm trying to stop this. Maybe here, maybe here. Yeah, maybe here. So you can see those vortices are generated when you have wave flow, but we knew that they will be always there when Kc is more than 5, and when Reynolds number is more than 1,000. We all know what Reynolds number is, but just to let you know that this length scale is the horizontal wave excursion length. The velocity is velocity far above the canopy, is the maximum velocity of the wave, and mu is the kinematic viscosity. Kc is Coulomb-Carpenter number. This is the ratio of inertia to drag force. So Reynolds number is the ratio of inertia to viscosity, right? Kc is the ratio of inertia to drag, because now we have drag of the structures, the roughness. All right, T, what is T? It must be wave period, right? U is velocity, and LD is the drag length scale. It is actually tells us, so if the canopy is very, very dense, LD is smaller because the stems are closer to each other. If the canopy is very, very sparse, LD is larger because stems are further away from each other. So when the canopy is sparse, LD is larger, Kc is smaller. Okay, so basically what this is telling us is that the canopy should be dense enough to be able to get those vortices. That makes sense, because if it's too sparse, there is no shear, there is no vortices. All right, I wanted to describe LD for you. Let's move on. Oh yeah, I would just want to say that's what we knew, but we didn't know how to predict mixing, and we didn't know if we can use unidirectional formulation in wave-dominated flow. So what I did, my work was purely experimental and analytical. So I ran experiments in this large flume. It was a wave tank at University of Western Australia. The width, 1.2 meters width, and you can see it was large enough that I had to swim in there to run my experiments. It was 1.2 meter depth, and I used these rigid dowels to simulate the roughness of the canopies. It's very common that people use these rigid dowels to simulate canopies. And then I ran my experiments for 4 different canopy densities, a lot of them. I think I had 10,000 dowels or something. Okay, what else? I used 3D ADV to measure my velocities and turbulence structures, and I used a dye injection system, as you can see here, to look at mixing of mass. So I actually measured mixing of mass by injecting rhodamine dye. I think that's all. If you have more questions, put it in the chat box and I will answer those questions. But I don't want to concentrate on the methodology. I'm going to show you some results. Okay, so what I did, as I said, I measured vertical turbulent diffusivity. This is how we measure mixing of mass. So DTZ is vertical turbulent diffusivity. And I scale my mixing, my vertical mixing, with shear layer mixing. So delta U LAD is how we characterize shear layer mixing. You remember those larger scale vortices? That's how we scale mixing in unidirectional flow. So I did the same. And what I found was a very nice collapse of data when I used this scaling. So I was very happy at the beginning, but then there was a bulge here. See, there is a bulge here in the right-hand side, left-hand side. Well, I thought maybe this is the uncertainty of my results. I wasn't really sure because R square was quite high. And to be honest, I first did my experiments for 3 and 5% because these are really representing most canopies. But then when I saw that bulge, like many of you, I was like, maybe I should repeat my test for very, very sparse canopy to see if I still see that bump there. I did it. A still nice collapse of data, as you can see, the white markers, but the bulge was still there. So then I had to do for 10% canopy, for very, very dense canopy, and I really didn't want to do that because making those canopies was very, very difficult. But again, I saw that bulge there. Then I thought maybe I need to rethink about my scaling. Remember how I talked about these larger scale vortices and smaller scale vortices? In unidirectional flows, we knew that wakes, these smaller scale vortices are not significant. But because of the nature of wave flows, I thought maybe they are doing something, this wake turbulence. So going back to this relationship, I thought when Kc is more than 5, and by the way, my Reynolds number was always more than 1,000, but my Kc were less than 5 and more than 5. When Kc was more than 5, yes, those larger scale vortices was present, so I could see mixing. But when the Kc was less than 5, I could still see that the dye was mixing. So how they were mixing, and it was much faster than molecular mixing. That must be because of those wakes. So that was another clue for me. So what I did, I was like, okay, let's go back. I collected all my mixing results with Kc less than 5. And I plot them as a function of wake mixing. This is how we scale mixing. And I saw this nice collapse of data. And then I realized when my Kc were more than 18, they are dominantly, mixing was dominantly by shear layer mixing, because when I plot them as a function of shear layer mixing, I didn't see any bump or bulge. The R square was quite high. So I think a lot of you now thinking, what happens when we are between 5 and 18? It must be a contribution of both of them, right? So that's what I also noticed, that yes, when we are between 5 and 18, then both of them should be equally important. Then I again looked at my data, mixing data, DTZ, as a function of both shear and wake mixing. And as you can see, there's a nice collapse of data. The bulge wasn't there, and we're quite happy. But also, we thought this relationship could actually hold for the entire range of Kc values, right? Because what happens is that, let's say when we are Kc is more than 18, even though shear layer mixing is a dominant process, it doesn't mean that the wakes are not there, it's still present. So we still should take them into account. They're just not the dominant process controlling wake mixing. So all of those details about Kcs are very exciting for us as fluid dynamics people. But for ecologists, that from me, they wanted one relationship that they can use and predict mixing. that relationship holds. So I use my vertical mixing, all my vertical mixing as a function of both shear and wake mixing, and very nice collabs with high square R squared I found. So the significance of this relationship was that we can actually rely on our understanding of unidirectional flow when we are looking at wave-dominated flows. Because as you can see, there are things that are important for wave-dominated flows, but they're not as significant in unidirectional flows. Anyway, that was a very nice piece of work for my first PhD paper. I published it in a nice journal, in Knowledge and Oceanography. If you have more questions or you want more details, it's my 2017 paper. All right. Then, when I was presenting my results, I always getting this question about people that you use these rigid dowels to simulate the roughness of canopies. But many of those canopies are flexible, like seagrasses, right? And many of corals are the soft corals, they move with the flow. So flexible vegetation, they move with the flow back and forth. It means that the height of the canopy is not constant. It means that the drag exerted by the canopy is also not constant. And they were asking me how your relationship would work in a more realistic or more flexible environment. And that was a valid question, right? And to answer that question, I decided to design some artificial seagrass, as you can see here, that they move and act exactly like a real seagrass. So they're not biologically active, but they behave exactly like the real seagrass. I have to skip the details of my design, but I thought for this community, I can quickly mention how I did it. So I looked at important forces that define plan motion, drag, buoyancy, and rigidity. So these are important, not all of them, but the important forces that we can use to define plan motion. And then I came up with this two-dimensional parameter, lambda1 and lambda2. And we all know that for dynamic similarity, lambda1 and lambda2 in the model should be equal to lambda1 and lambda2 in the prototype. My model, I ended up using LDPE. I've been looking at different materials, but I've been ended up using low-density polyethylene, which had the same density of seagrass and water. And then for prototype, I looked at Posidonia australis. I had two ecologists to tell me why. Yeah, and that's what I did. I measured lambda1 of Posidonia australis, which was around 0.1, around, because we can't really say it was exactly 0.1. It was a range around 0.1. And then for my blade, I made some of these blades with a range of lambda1 around that blade. And then I exposed them to different wave conditions. And as you can see, this one near the real Posidonia australis, this one is behaving very similar to the real blade. I have another picture showing that how well actually this blade behave, very similar to the real plant on the different wave cycles. This is going to be this is on the trough. This is on the crest. This is on the trough. So anyway, on the different wave faces, I have a video to show you. So this is my densest canopy, this 10% canopy. Posidonia australis has two blades, one longer, one shorter. Some of them they have three blades, but mine they all have two blades. So what I did, I cut them with the guillotine, 16,000 of them, cut them, put them together, and I wrapped a very small rigid dowel to simulate the stiffness of the stem. I'm not sure if you can see, but down here. And then I hammered them to perforate. And I made 4 different canopy densities. So similar to rigid canopy, to be able to compare these two canopies. Okay, time to see some comparison. All right, what I'm showing here is one canopy rigid on the left-hand side, one canopy flexible on the right-hand side. These two canopies are exactly the same. The height is the same, 30 centimeters, when the canopy is upright. The frontal area of these two canopies are the same, and I expose them to the same wave conditions. So this is one example actually. So everything the same, and I'm going to show you some results. This is velocity profile. I start with velocity profile. And the left-hand side, I'm showing rigid canopy, and right-hand side is flexible. This is velocity. This is height from bed to the water surface. 30 centimeters at the top is the top of the canopy. The black line is the dense canopy. The gray line is the sparser canopy. As you can see, the flow far above the canopy was the same, so I just exposed them to the same flow condition, around 20 centimeters per second. The in-canopy velocity reduces from above canopy velocity, which is not surprising, but then you can see that the reduction in the sparse canopy is less, because the sparse canopy exerts less drag, so reduction of the velocity is less in these canopies. Now, when we look at the flexible vegetation, at first, they don't look similar at all, right? But when we look more closely, we can see that there is actually a reduction of velocity within the canopy. This region here is actually top of the canopy in flexible vegetation. This is actually where the canopy was bent over. So what this tells us is that within the canopy, where the canopy is upright, like the first 10 centimeters of the canopy was upright because the rest of it was moving with the flow back and forth, those upper parts was not exerting any drag because it was moving with the flow back force. So that's why there is no reduction over there, but those rigid part or those upright part, they are exerting drag, and we can see reduction of velocity. So that's how flexible vegetation change flow conditions. And there is a shear, but the shear is not as strong as rigid. Again, makes sense because the canopy is moving back and forth in that region. Now that we're talking to fluid dynamics people, I think you would like to see some turbulence as well. Okay, so I'm showing a color map. All on the left-hand side, this is all rigid, this is all flexible. The first one is the velocity, non-dimensionalized velocity. This is the wave face. For some of you that are not familiar with the waves, just look at this part because that's where we have velocity, like the heart, or on the crest. 30 centimeters is the top of the canopy. As you can see, inside the canopy, velocity is less than above the canopy. There is a shear at the top of the canopy. We saw that in the previous slide as well. The second one is more interesting because that is color map of U''W'. U''W' is actually telling us about vertical mixing because this is vertical mixing of horizontal momentum. So, when U''W' is negative, we are actually getting some vertical mixing. And as you can see, there's a peak at the top of the canopy. So even though I haven't seen visually, you can see those vortices, these strong mixing at the top of the canopy is a signature of the presence of those vortices. And I should say this result that I'm showing for the case in more than 15. So we know that those vortices are present. Anyway, the last one is TKE. We can see increased TKE within the canopy and the peak of TKE at the top of the canopy. Again, because of those vortices. The right-hand side, everything is very similar. It's just everything being shifted down now, and you are very familiar because we have seen the previous slide. So the shear layer is here, and then we have strong mixing at the top of the canopy. But now for flexible canopy, everything is happening very near the bed, right? So if you look at the TKE, there's strong turbulent kinetic energy very near the bed. So even though this color map was very exciting for us as fluid dynamics people, but the color was also very important because what this tells them is that when we have flexible vegetation, we may have this turbulence may significantly contribute to the mixing from the soil, from the seabed to the water column. And that region is extremely important for ecologists in terms of flux of materials and nutrients and all of that, oxygen and carbon and all of that. and also for suspension of sediment as well. Okay, we are going to look at some mixing results, actual mixing of mass, because what this one tells us is mixing of momentum, but I did actually measure mixing of mass. Okay, so what I did, I plotted the mixing that I got from flexible vegetation, and I compared them with the mixing of rigid canopies. So everything is the same, canopy is the same, and flow conditions the same, and everything the same, but one of them is flexible, one of them is rigid. And as you can see, rate of vertical mixing was always less in flexible canopies compared to corresponding rigid canopies, something around 30 to 35%. So this is will not be good news for numerical modelers in particular, because it's very difficult to use flexible mesh and flexible models. But my results here is showing that if we are going to use model seagrass or model, I don't know, corals where they're flexible, we need to make sure that we are considering the impact of flexibility. It was difficult for me as well, because, you know, making those canopies was difficult. In the lab, doing the measurements, just imagine I had the AVD and the flow was going back, forth, and they were hitting the AVD. So how much noise I got when I was doing flexible vegetation, which none of them exist when I was doing rigid canopies. And also just the analytical model, what is the height of the canopy? The height of the canopy changes over time. The drag changes over time. But that's the result that I got. So, of course, I had to modify the model that I presented in the first paper as well. So I also modified the model a little bit just for flexible vegetation, and the results, I published this one also in Limnology and Oceanography, if you are interested to see more details about how overcome some of those challenges. It's also in the paper as well. Okay, so there were 2 more papers out of that PhD, which was a very fruitful PhD. But I thought I would just move on and talk about some of the postdoc projects that I did, and again, how I use my expertise in different projects. The first one that I would like to talk about is sediment transport, because as you notice, I didn't have sediment in my lab or in my experiments when I was doing my PhD. So in my postdoc, I was looking at sediment transport in Canada. Because what we have, the model, I'm not sure how many of you have done sediment transport, but the model that we have, I'm sure you should be familiar with Shields diagram. We use Shields diagram to predict sediment transport, but Shields diagram being developed for a bare bed, like flat, sandy bed. But again, in the real system, we have seagrasses, we have bed form, we have roughnnesses, and almost many of our numerical models, or maybe all of them, they're using Shields diagram. They don't have the impact of vegetation because we still don't know how vegetation impacts on sediment transport. This is a very hot and important topic to work on. And also, you already know that how things are complex when we have canopies. We have these large scale vortices, we have these waves, they may penetrate to the bed and they may contribute to the resuspension of sediments, especially when we have flexible vegetation. So things are very complex. And in that project, I had 2 PhD students, and I ended up being more involved in the laboratory testing. So one was focusing on lab testing, one on field measurements and observations. We used high resolution PIV to focus on near-bed region to look at how shear stresses and turbulence changes. And then we have canopies. We looked at emergent and submerged canopies, but all rigid. Anyway, both of them are finishing. As I said, I was more involved in the laboratory testing, but hopefully soon we'll see some papers out of this work, and yeah, it's nice to see. Okay, I thought I'm gonna talk about another project that you are familiar now about, those artificial seagrasses. So I designed them as part of my PhD project. I think I designed them within 3 or 4 months, within the first 3 or 4 months of my PhD project. But they become a very important part of my career because people just love them. And doesn't matter how much I talk about turbulence, they always talk about those vegetation. So if you have any questions, put in the chat box. I am I'm ready and happy to answer those questions too. Anyway, so I've been using those seagrasses for a variety of projects. And now that people are more keen to use natural-based solution for engineering problems, so even it's a very hot topic, so I've been using for natural, again, as a natural-based solution for coastal protection or riverbank protection when we have flooding and storms, and also revegetation. So I'm recently got a funding to use them as revegetation. And also I use, I've done a bit of research of using them for scour subsea pipelines, which I thought you might be interested to listen about it. So I have one slide to describe that as well. We could use them for a variety of problems in subsea structures, but I'm just putting an example of lateral buckling. So lateral buckling is a very common phenomenon, happens in subsea pipelines because of the temperature goes up and the pipeline length increases, and then the pipeline starts moving and walking laterally. There are a number of solutions for that. People use these displacement initiators, or they may use large mattresses, concrete mattresses or galleons to just stop them. But I thought if seagrasses are that helpful to trap sediments, why don't we use them to help with scour subsea pipelines? And I did a bit of research and I realized that people are actually using them. So this is one example of successful usage of those artificial seagrasses. They call them front mats. You may have heard them as front mats. But the problem is that they're not always helpful, because it's not surprising for me, because we still don't know how seagrasses impact on sediment transport. They may increase or decrease sediment trapping. So we don't have that predictive capability yet. And the project that I did with my students is actually basically the same question that we are going to answer. But there are a lot of companies, they're selling this from us and they're claiming that they're going to trap sediment. But the reality is that we need a design guideline. So this is an ongoing research. My goal is to come up with a design guideline. So if you tell me what is the hydrodynamic conditions, what is the sediment properties, then I can tell you what small mass with what height, density, thickness, flexibility you can use for that particular flow and sediment conditions. It's also very complex, but there are a lot of interest in this area at the moment. So yeah, I'm working on that parallel to other projects. And finally, I'm going to talk about my research project, which is a bit different. It's still hydrodynamics, but it's a bit different. It's about VIV, vortex-induced vibration. For someone who is not familiar with, I think most of you don't know the names, I think you are, but if we have a cylinder and the flow is going from left to right, we get this nice vortex shedding behind the cell that we all love to watch them. But if the frequency of that vortex shedding is matched or even close to the natural frequency of the cylinder, then the cylinder starts vibrating. Sorry, this is just a gift that I found online, so I didn't have to worry about the copyright. So anyway, so the cylinder start vibrating, and at some point, depending on your radius velocity and all of that, the amplitude of the vibration is very, very large when you are on the left and right. But for many structures and many conditions, that's not something that we want. So we really want to be able to predict it and to be able to avoid it. The same thing happens in subsea pipelines, because again, pipelines are not always laying down on the floor and they're in the ground, because the seabed can have bumps, can have red forms, and Sometimes we have very large spans. We have guidelines for the maximum spans, but it should be, because if the span is very large and then the pipe will start sagging and the friction becomes important. But then if it's very large and then we have vibration, it causes fatigue in the pipeline. This is a very important phenomenon that we really don't want this in pipelines. And if we have a mobile bed, that vibration would impact on the rate of scour and sediment transport as well. So it becomes a really, really complicated problem, but we really don't have a good understanding of this phenomenon. So yeah, what I'm doing in this project is just some experiments to look at VIV with different flow conditions and sediments. So I'm looking at VIV and sediment transport in the laboratory. I've just started this project, so I don't have results to show you, but I thought it would be interesting to show you how, again, I use my expertise in the area of turbulence and vortex structures and sediment transport in subsea structures. That was my presentation for today. I hope it was interesting for you guys. If you have any question, I haven't seen the questions, I can't see them now, but I'm happy to answer questions if there is any.